In business, you're constantly up against complex problems, right? Problems where so many different things influence your bottom line. And look, the wrong decision can cost you millions, but the right one? That can unlock some serious growth. So today, we're not just going to talk about a framework. We're going to break down a systematic way to get to the right answer faster. It's called Factorial Design.
So here's how we're going to tackle this. First, we'll nail down the exact problem this is all built to solve. Then, we'll define what factorial design actually is. From there, we're going to do a deep dive into the two main strategies you can use. After that, we'll talk about a critical risk you've got to watch out for. It's called confounding. And we'll wrap up with a pro-level technique to handle that risk, a method called blocking. Let's get into it.
All right, let's start with the big challenge. Why do we even need a special way to design experiments? Well, it all comes down to one thing: untangling complexity.
Think about it like this. Say you're trying to create the perfect recipe. You've got different flours, different amounts of sugar, different baking times, different temperatures. So how do you find that perfect combination? The way most people do it is they test one thing at a time. First, you tweak the sugar. Then you tweak the flours. But we all know it's not that simple, is it? And this isn't just about cooking. It's about optimizing marketing campaigns, or supply chains, or manufacturing. When you've got a ton of variables in play, that simple, one-by-one approach doesn't just fail to find the best answer. A lot of the time, it leads you to the wrong one.
And that's because testing one factor at a time has two huge flaws. First, it's just slow and inefficient. You could waste months tweaking little things without ever getting close to the best result. But the second flaw is way more dangerous. It completely hides how these factors interact with each other. Maybe that new ad copy only works with a specific audience, or a change in your supply chain is only a good idea if you also change your software. Testing in isolation will never, ever show you these game-changing relationships. And those interactions, that's where the real magic is hidden. The old way makes them impossible to see.
And this is exactly where our framework comes in. Factorial design gives you a structured way to see not just the individual ingredients, but how they all work together to create that final result.
So what is it really? At its heart, factorial design is a systematic way to experiment. You set up your tests to check every factor you care about, all at the same time. And the result is you can measure the main effect of each factor, sure, but way more importantly, you uncover how they interact. And trust me, those interactions are almost always where the real breakthroughs are hiding. It's a huge mindset shift, from thinking in a straight line to thinking in systems, and recognizing that in any complex setup, things rarely work in isolation.
Okay, so once you decide to use this framework, you're faced with a big strategic choice. There are two main ways to do it, and the one you pick has major consequences for your time, your budget, and, of course, the quality of your results.
So on one hand, you've got what's called a full factorial design. This is the exhaustive approach, where you test every single possible combination. On the other hand, you have a fractional factorial design. This is more of a surgical strike, where you test a carefully chosen, smaller set of combinations. And right there, that's your first major strategic trade-off. A simple way to think about it is this. If the cost of getting it wrong is incredibly high, we're talking medical devices or pharma trials, you're going to lean towards full factorial. You need absolute certainty. But if you're in an early exploratory phase, like optimizing a web page or tweaking an internal process, a fractional design is your best friend. It gives you the most bang for your buck, letting you learn and iterate super fast.
Let's really break down this trade-off. A full factorial design is incredibly thorough. It gives you this high-resolution map of every single effect and interaction. You miss nothing. The downside, of course, is that it can get insanely expensive and time-consuming. With just 5 factors at 2 levels each, you're already running 32 tests. 10 factors? That's over 1,000. Now, a fractional design is way cheaper and faster. It might take those 1,000 runs and cut them down to 64, or even 32. The savings are just astronomical. But that efficiency comes with a price. You might miss some of the more complex interactions, and more importantly, you introduce a serious problem called confounding.
So, you've decided to go with the faster, cheaper option, a partial design. Great choice. But now you have to actively manage its biggest risk, and that risk is confounding.
Confounding is pretty much exactly what it sounds like. Your results get confused. Because you didn't test every combination, the effect of one thing gets tangled up with the effect of another. For instance, say your marketing team tests a new headline and a new audience in a fractional design. Sales double. Awesome, right? But was it the brilliant new headline or the perfectly targeted new audience? With confounding, you just can't be sure. The effects are aliased. They're mixed together. Your data is ambiguous, your conclusions aren't reliable, and that multi-million-dollar rollout is now basically a guess. So how do we deal with this? How do we get the efficiency of a partial design without falling into that confounding trap? Well, this is where the experts use a technique called blocking. It's the pro move for getting clean, reliable results.
Blocking is all about isolating and neutralizing the effects of variables you're not actually interested in, but you know could mess with the results. We call these nuisance factors. For example, maybe one batch of raw materials came from supplier A and another from supplier B. You don't really care about the supplier for this test, but it might affect the outcome. Or maybe your experiment has to run across 2 different shifts with 2 different teams. By grouping your test runs into blocks, one for each supplier or one for each shift, you can mathematically subtract that noise from your final analysis. You make sure it doesn't contaminate your real findings.
And the process is actually pretty straightforward. Step 1. You identify one of those nuisance factors. Let's say you're running tests on 2 different machines, an old one and a new one. Step 2. You create a block for each machine. Step 3. You run your main experiments within each of those blocks. And this is the key part. You run a balanced set of your experiments on the old machine and another balanced set on the new one. And finally, step 4. When you analyze the data, you can cleanly separate the effect of the machine from the effect of the factors you actually care about. You've isolated the signal from the noise.
And that, right there, is the entire goal. Blocking is your insurance policy. It guarantees that when you make a conclusion, it's about the variables you meant to study, not some hidden factor you forgot to account for. It brings clarity and confidence back to your results. It's the difference between making a guess and making a confident, data-backed decision. So, we've covered a lot of ground here, right? From the core problem all the way to an advanced technique like blocking. But why does any of this actually matter to you in a practical sense?
Here are your key takeaways. Number 1. Stop testing variables one at a time. Seriously, you are flying blind to the most critical insights and you're leaving your biggest opportunities on the table. 2. Be deliberate about your strategy. Consciously make that trade-off between the speed of a fractional design and the certainty of a full one. 3. If you choose speed, you must actively manage the risk of confounding. Hope is not a strategy. And 4. Always use a structured design to get clear, confident answers for messy, complex problems.
So I'll leave you with this question. What critical problem are you trying to solve right now, piece by piece, when the real breakthrough is just waiting to be found in the interaction between all those pieces?